What is a black hole? I just thought this picture was way too cute. It's when you try to put too much stuff into too small a space. Duh. Okay, so let's talk a little bit more about the physics. Imagine we could squish the Earth into a smaller space. You know, we put on our Incredible Hulk gloves. Do we have any Incredible Hulks in the audience? Okay, it's all right. It's all right. Imagine we could put on our Incredible Hulk gloves and squish the Earth down to a smaller size. What would happen? What would our theories of gravity tell us would happen to, let's put on our thinking caps and do a little bit of a thinking experiment, a thought experiment. What we're going to do is we're going to stand on the Earth and we're going to point our rifle upward, okay, our high-powered rifle upward. We're going to shoot that bullet out the high-speed rifle. And question, you shoot even with the highest speed rifle out there, you shoot the bullet, is it going to escape Earth's gravity? Or is it going to go up into the atmosphere and eventually turn around and come back down to Earth? The second one, right? Absolutely. Turns out, you do the math, you need a bullet to travel about 10 times faster, which is actually a little bit surprising to me. That's really fast. The highest speed rifle muzzle velocity is about 2,500 miles per hour. To escape Earth's gravity, you just need to be 10 times faster, okay? Now, what happens to the escape velocity of Earth? That is, how fast a bullet would need to travel to escape the confines of Earth's gravity and float off into interplanetary space. If, let's say, the Earth were squished to half its size, a very interesting thing happens. It increases to 35,000 miles per hour. Let's go a little bit crazy here. Let's go to 1/100th the size. 250,000 miles per hour would be necessary. That's 10 times the normal. Now, let's keep going, getting crazier and crazier. If we could squish all the Earth's mass into the size of a basketball, the speed necessary to escape from the surface of that basketball-sized Earth to get into outer space, interplanetary space, would be 180 million miles per hour. Now, as we keep squishing, something very interesting is going to happen. Very interesting. We get down to about the size of a golf ball. And suddenly, everything goes dark. Because the speed that you need to shoot a bullet to escape the Earth's atmosphere, to escape from Earth's gravity, would exceed the speed of light. So not even light could escape an Earth the size of a golf ball. And that's what we call, my friends, a black hole. When the speed needed to escape something in space exceeds the speed of light, we call that region inside a black hole. But we know that there aren't cute ladies wearing Incredible Hulk gloves in space creating black holes for us. At least we have some confidence in that notion. How are black holes naturally formed? That's an important question that we should look into. They form when gravity overwhelms all other forces. By that I mean there's a natural, completely out of control squishing that just takes place naturally. Let me introduce you to a very, very massive star. This star has a mass of somewhere between 60 and 80 times the mass of our sun. Such stars live very short lives. They burn bright and they die young. And like our sun, there's a balance. While this star is alive, there's a beautiful balance. The heat from nuclear fusion, the same process, by the way, that's behind hydrogen bombs, pushes out. All that heat pushes out, but gravity pulls in, and the whole system is in this glorious balance. Well, kinda. So our sun, as many of you may know, will fuse hydrogen into helium. But that's it. These really massive stars, they're so hot, they can fuse helium into carbon, carbon into oxygen, all the way up to iron. Something very special about iron. Iron doesn't fuse. It doesn't release energy when it's fused with another nucleon, another, say, neutron. So you can think of the core here, which is made a big ball of iron, basically, as kind of like nuclear waste, right? It's the waste product of the fusion process. The thing is, though, as this nuclear waste ball grows and grows, eventually, and by the way, it's pushing back, not from heat. It's pushing back by basically the same physical principle as when I push down on this podium, it pushes back at me. So it's kind of like a solid surface. But the thing is, solid surfaces are only going to be able to support so much weight, especially if that surface itself is growing. In fact, what will happen is, when that iron ball gets too big, it actually collapses under its own weight into a black hole. It's a runaway process. And it takes course over the process of milliseconds. And those outer layers, by the way, rich in thermonuclear fuel, fall onto that black hole. The black hole can't gobble up that matter fast enough. And what ends up happening is a shock wave propagates out from the center through all that thermonuclear fuel and ignites, generating one of those spectacular explosions in the universe, a supernova. And at the center, a black hole. In this supernova, by the way, a huge amount of heavy elements are ejected. Oxygen, carbon, iron. Very interesting. This, my friends, is what we think all the iron on Earth came from, supernova. Maybe not from stars quite this mass, because they collapse. The iron core tends to collapse to a black hole. But supernova more generally. And this really big star that has now collapsed to a black hole, that could be a mass of around 36 times the mass of our sun, let's say. That's about 66 miles in diameter across its what's known as event horizon. Bring that a little bit closer to home. Here we are, the center of this circle. There's Sand Point. Maybe you can see a little bit of the stuff on here. But here's the panhandle, the left wing of the panhandle, the west. Here's the east wing of the panhandle. That's 36 times the mass of our sun in a tiny sphere with the same diameter as this circle. How crazy dense black holes are. And just so we're clear on definitions, black hole is a place where gravity is so strong, light can't escape. I think we've all gathered that at this point. But the thing is, we call the surface of this region the event horizon. So if you're inside the event horizon, the escape speed is beyond the speed of light. You're never getting out. Sorry. If you're outside, you have to be moving pretty darn fast if you're close to the black hole to escape its gravitational field. Another important fact, black holes are dark, so they're very hard to detect generally. Question I often get asked, so I'll go ahead and answer it right now. What happens if you fall into a black hole? Well, has anyone seen this old movie, Aladdin? The old Disney movie? Great. So you know when Aladdin rubbed the side of the lamp, the genie popped out? And I love this animation because it's so backwards in time, let's just say, going into a black hole. So what happens when you get close to a black hole is, let's say you're going in feet first. Your legs are going to get squished and they're going to get stretched. Doesn't that look familiar? Just like that. Kind of cool, huh? It's a process that has a scientific term. Remember this, spaghettification. No joke. That is the scientific term. Take it from me. So this is basically what it would look like if, you got too close to a black hole. Although this is heavily censored, there would normally be a lot of, gore and, stuff like that. But wait a second, you should be asking, this is a talk about black holes colliding, not just about single black hole. Fair. Let's talk about that. Why did I say neutron stars? Sorry. Black holes. Black holes are tiny compared to the average distance between stars. My goodness, they're like 36. How many miles across did I say? There you go. 66 miles in diameter. 33 miles in radius. For goodness sake, that's tiny, especially compared to the distance between stars in our galaxy, right? The nearest star is like a light year away, the distance that light travels in a year. That's really far. So how could you possibly get two tiny things to collide in our universe? Turns out it's not too hard to believe because most of the stars in our universe actually closely orbit another star. It's known as a binary star system. So, very simple story. You just start with two really huge stars that are orbiting. They'll go supernova, and you end up with two orbiting black holes. Voila. Well, wait a second. Now you go back, look at your old elementary school textbooks where you learned about Newton's theory of gravity, the inverse square law, right? We all learned this, when we were in elementary school, right? I'm just kidding. Okay. No. According to Newton's theory of gravity, there's no mechanism. There's nothing that's going to cause these black holes to collide. They'll just keep orbiting forever and ever. Well, turns out Einstein stood on the shoulders of Newton. What a funny way of putting it. How ironic. And saw farther. Einstein's theory of gravity is our best understanding of gravity. Newton's theory has been disproven. And Einstein's theory of gravity, predicts some amazing phenomenon known as gravitational waves. These gravitational waves, they take away the energy, the very energy keeping the two black holes apart as they orbit. So what do? They in-spiral, just like this. It's called in-spiral, by the way. And what we get is a relativistic, because Einstein's theory of gravity is called general relativity, okay? It's a relativistic death spiral to collision. Also because they're moving close to the speed of light, like between a tenth and 30% of the speed of light right when they're coming together. But gravitational waves are so important because this is the only means we have to ever possibly see this merger. These two black holes coalesce. It's almost like we're doing an X-ray of the system. And in fact, the first ever detection of gravitational waves by our gravitational wave telescopes was a detection of two colliding black holes. The amount of energy released in gravitational waves from that merger, from that collision, if you had converted that into light, it would have been brighter. It would have produced more light than all the stars in the known universe combined during that time. We're talking taking something like 3 of our suns and turning it into pure energy. That's how much energy is in these gravitational waves. Lucky for us, because gravitational waves are very weak. They very weakly interact with matter. Like, we don't notice when a gravitational wave is passing through us, but they are. And I'm so proud to say, we're now, since 2015, we're something like, 8 years now? Just past 8 years into the new era of astronomy known as gravitational wave astronomy. We've now seen dozens of colliding black holes. This is a fun little picture here. So as you look up here, that's higher and higher mass. And you notice there are always 2 dots connected by a line, and then there's an arrow. So the 2 dots indicate the two, if they're blue, they indicate 2 black holes, and then the arrow indicates the mass of the final black hole. Something very interesting, if you add up the 2 masses of the individual black holes, it's never twice. This is never twice that. It's always a lot less because, like I said, huge amounts of energy are lost in that merger. So here's a census of current detected gravitational waves from colliding black holes. By the way, these orange dots are neutron stars. Another very interesting thing, but that's a talk for another day. Black holes, okay? Here's a story. They orbit in space. They emit gravitational waves. The waves carry energy away from the black holes, the very energy that keep them apart, bringing them closer and closer together. The waves get stronger and faster, leading to a runaway effect that causes them to collide and merge into a single, very massive black hole. Please remember this. Gravitational waves are a scientific treasure trove containing important information about these black holes. Information that it would be impossible for us to know. But how do we get the information out? Nature gives us a wiggle. How do we extract information from that wiggle? Well, we compare it against millions of theoretical predictions to extract the essential science from the wave. To, for example, get an idea of just how massive each of the black holes were. and how fast each of them and in what direction each of them was spinning. Very interesting thing. Black holes, it turns out, seem to be very simple objects. You can describe them with two quantities. Their mass, how heavy they are, and their spin, how fast they're spinning. Kind of interesting. And by comparing the observed gravitational wave against many millions of theoretical predictions, we can actually pin down, according to Einstein's theory of gravity, how fast the black holes were spinning and their masses, which tells us a lot about how they came into being. These theoretical predictions themselves are built upon catalogs. Remember that beautiful picture I showed at the beginning of my talk? This is actually a visualization of an actual simulation that was performed of two colliding black holes. These theoretical predictions are built on these catalogs, performed by solving Einstein's equations of general relativity on supercomputers. That's the science that I do. And my science is under threat right now. We're working on building the next generation of gravitational wave telescopes. And those telescopes are going to be so sensitive that we are going to need much larger and much more accurate catalogs of simulations to compare our observations against. What do we do? Well, I've undertaken in my research group over the past 5-6 years to develop new techniques that will enable us to simulate colliding black holes in such a way that they reduce computational expense and improve accuracy. So it's double difficult. Now, normally, what we would do to improve accuracy is we just increase the cost of our simulation. Thank you. We just increase the cost of our simulation. We'd run it on a bigger supercomputer. And then maybe we get a little bit more accuracy. My goal is to go the opposite direction. Improve accuracy while reducing computational expense. So I put a lot of thinking into this. And as my family can attest, this has been an absolute challenge. But it's like John F. Kennedy said, we don't do this because it's easy. We do it because it's hard. Because it's a challenge. And by golly, the part of the challenge you overcome, the sweeter it is when you prove your detractors wrong, right? I'm just kidding. Anyway, could someone click play on this? All right, so using my new technique, here is a black hole collision simulation. The dark dots are black holes. The black holes are just undergoing their final orbits before they merge into a single black hole. This is a very important simulation, it turns out. This was one of the first ever black hole collision simulations ever performed. But I reproduced it using my new technique. I wouldn't be showing you this unless I had compared my new technique against a trusted result that used a supercomputing cluster. And you can see there's a red and blue line here. It's hard to tell, but they overlap so darn well that you can't even tell the difference. I don't know. It still amazes me that how good this looks. Like I said, the trusted result was run on a supercomputer. My new technique, which I'm trying to decrease the cost of the computation, turns out, happy to report, didn't require a supercomputer. Yay! It actually didn't even require a desktop computer. I did the darn thing on my cell phone. First time ever. I swear to you, someday that cell phone will be hanging on the walls of the Smithsonian. Anyway. But let me just say something, all right? Just to clear the air. I am not intending for my project to be run on cell phones. Please don't do that. This poor cell phone, it died like 2 months later. Cell phones are just not meant for heavy computations. I mean, duh. Most of you are probably thinking, duh, what is this guy thinking? Think he's doing black hole simulations on his cell phone. But let me tell you, in terms of a proof of principle, there you got it. And here it is, by the way, running on my cell phone. Pickard didn't happen, right? Yeah, poor cell phone. Anyway. All right, so this gets me to the last slide of our talk. So what I want to do with this project since it is now possible to do these black hole collision simulations on consumer-grade hardware, not cell phones, more like desktops, laptops, tablets, I want to launch a volunteer computing project. I'm going to need your help when this project launches to help me generate catalogs of simulations for the benefit of gravitational wave astronomy. And with that said, I'd be happy to take any questions. Thank you so much.